Hello and welcome back. You're talking about a new section, 2.2, Techniques of Differentiation. Remember, differentiation is just the verb that we use to say, I'm going to take the derivative of blah. So this section is about some helpful rules that we can use. So this first video we'll talk about using the constant multiple rule, sum rule, and power rule to find derivatives. These are often referred to as shortcut rules. So, derivative rules. Remember, we defined the derivative in the last section, and it's basically this rate of change at a point, and we had this big, nasty limit as some slope fraction goes to zero kind of deal. And what we'd like to avoid is having to use that all the time. So we have our handful of rules that get us around having to use that big limit fraction. So if c is some constant, then we can say its derivative. And part of what's going to take a little bit of getting used to is this notation right here. But that ddx thing is just supposed to tell us take the derivative of whatever is to the right of me. So in this case, take the derivative of c. And so what this rule is telling us is that if you have the derivative of a constant, you should get 0. And maybe this makes sense. If you had the line y equals 4, for instance, some constant, then its slope is 0. Horizontal lines have a slope of 0, and a derivative is just a slope. Okay, maybe more exciting, this is usually called the power rule. If you have x to some constant number, and this could be any real number, positive, negative, fractions, irrational numbers, weird stuff. It looks like n, so that exponent, times x to the 1 smaller than what it used to be. And we'll do some quick examples here in a sec. One more is that if you have any kind of function you're taking the derivative, anything with x's in it and it's multiplied by some constant, you can just sort of ignore the constant. You could think about pulling this outside of the fraction, if you will, or outside of the derivative expression, and just doing it later. So here it is sitting outside, and all that's left inside is the thing with x's on it. And ideally, it'll look like x to some power, so we can now break that down into, further into a power rule. And then the last thing also looks a lot like our limit expressions. If we take two functions, two things with x's in them getting added or subtracted, then you can deal with the derivatives after the fact. So we can take the derivative of one, take the derivative of the other, and then just add the results, sort of like what we do with limits. So to put these in words, the derivative of a constant function is 0. Slope of a horizontal line is 0. The derivative of a constant times some function is just the derivative of that function with the constant outside. Just delay it, wait until after you've already computed the hard stuff. And then if you add or subtract two functions, then you can just take the derivative of each one of them and add the results together, or subtract, as the case may be. So some quick examples just to get us feeling what's going on here. Derivative of 7, for instance. So this function, just the constant function 7, has a slope of 0. So its derivative is 0. One of the more exciting ones we've got, if our expression looks like x to the some kind of power, the way I like to think about this is that this 2 is essentially, when we take the derivative, this 2 is coming down out in front. So there it is now. And then our exponent gets reduced by a power of 1. So what used to be 2 is now 2 to the x to the 2 minus 1, or x to the first if we really wanted to. So this is a much quicker version than what we were doing in the last section, and it turns out this rule holds no matter what. So anytime we run into x to some power, we can use this power rule to bring that exponent down and reduce the power by 1. One more. So this is using that constant multiple rule. If we have, in this case, it's 6 that's being multiplied to the x stuff, then that 6 can come out in front, just leave it off till the end. And what that lets us do is focus just on the x to the 2/3 piece. And this is where we can make use of our power rule from up above. If we have x to the 2/3, then we can take that exponent, pull it out in front as a multiple. So there's the 2/3 coming out, and then decrease the power by 1. So if you notice in this case, since we started with 2/3 and took away 1, we should end up with something negative by the time we're done. So 2/3 minus 1 is a negative 1/3. And this whole expression is the slope at any value x of this function, which is pretty handy. Okay, so let's try a more elaborate example, slightly more elaborate. So we're computing f prime. Remember, f prime just means the derivative. So this just says find the derivative of f when f is this function. So I'm going to piece this out a little bit more into bite-sized chunks than I probably will in the long run, and definitely more than you will show on your work. But I just want to illustrate all the rules that we're employing here. So one note, we could go back to our definition from the previous section and do limit as h goes to 0, f of x plus h, yada, yada, yada. But then we'd be doing all this crazy stuff with square roots and conjugates and canceling, and it's more work than is necessary. So we can actually shortcut this pretty substantially by using the rules from this section. In particular, first, the difference rule. So the way I'm going to try to think about this is that the last operation, the last thing that happens in this expression is the subtraction. If we actually had a number for x, we'd take the square root of it, we'd take 2 times that number, and then the very last thing is we would subtract 1 from the other. And that's what the derivative focuses on first. It sort of looks at the last operation, subtraction in this case, and that's what it needs to deal with before it gets any further. So since we can subtract pretty easily with the derivative, we just break this thing up into 2 separate derivatives. Notice that each of them still has this instruction on it. This d dx is take the derivative of whatever is to the right of me. So this derivative, this is asking to take the derivative of 2x. This is asking to take the derivative of square root of x. So all we've successfully done is taken this big expression and broken it into 2 smaller ones, ideally ones that are even easier to tackle. So continuing on, if we look inside of each of these, maybe at first glance this looks impossible because we say, oh look, it's a square root of x, that doesn't look like anything we've run into before. But remember your fraction exponents. Square root of x is the same as x to the 1/2 power. And that's actually a great place to be, because if you have x to some number, some constant, we can make use of that power rule that we were given. This doesn't quite look like x to some power, but it's close enough because we've got that constant multiple rule, which would allow us to take this multiple of 2 and bring it out in front. And maybe I'll even trace it all the way down to here where we actually do it. So the 2 comes out in front of the derivative, and now we're asked to take the derivative of just x. And for simplicity, or maybe just to note that what we've got really does look like power rule, plain old x by itself really is x to the 1st power. And so the 2 things that we have left to tackle, x to some power, x to some power, look exactly like what our power rule is ready to deal with. So we could finally make use of power rule. The 0.5 comes out in front as a multiple, and then we decrease that exponent by 1. And then the exact same thing happens over here. We'll bring the 1 out in front, but of course multiplying by 1 isn't really going to change this at all. And then we decrease that power by 1. So what we get is something a little bit weird, but remember x to the 0th power is just 1. Anything to the 0th power, we have to be careful, anything other than 0 to the 0th power is just 1. So this would really look like 2 times 1 when we're all done, but that's just 2. And then we've got this factor, so x to the, it turns out, negative 0.5 once we do the subtraction. That's the only piece where x's are actually involved in our function. And then maybe just one reminder before we call this quits. Basically, this derivative operator sticks around as long as is necessary before we actually compute the derivative. So here, the last thing that we really did was use the power rule to turn this whole expression into the slope of that function. So in this second to last line, there are no more d dx's because we actually applied the rule. We actually found the slope of this function inside. Everything else was just sort of delaying the inevitable, breaking this up over subtraction, bringing out the 2. All of those were kind of secondary rules that got us down to the real one, which was power rule, that actually let us figure out the slope of these 2 expressions. So I'm sure it will be it will take us some work to get used to this, but this d dx is only around while we still have yet to take the derivative. It goes away as soon as we actually apply that rule. So we'll do another applied example in the upcoming video. I'll talk to you then.